This diagram changed the world. Before 2017, NLP was dominated by RNNs and LSTMs. They were sequential, meaning token 2 waited for token 1. This made training on massive datasets impossible. Then came Attention is All You Need by Vaswani et al. They proposed a radical idea: forget recurrence. Instead, let every token attend to every other token simultaneously. This specific architectural diagram, the encoder on the left, decoder on the right, is the blueprint for GPT-4, Claude, and Llama. But most engineers treat it as a black box. Today, we open the hood. We are going to implement the encoder block from scratch in PyTorch, not just to copy code, but to understand why it works. We start with the init method. The heart of the transformer is multi-head attention. Think of this as the social layer. In a room full of people, tokens, everyone is talking. Attention allows each token to focus on the relevant ones. We pass embed_size, usually 512, and heads, usually 8. Why heads? Because language is multifaceted. One head might track syntax, another semantics, another rhyme. By splitting the embedding into 8 subspace streams, the model captures these distinct relationships in parallel. We also initialize layer norm. We use layer normalization instead of batch normalization because in NLP, batch statistics are noisy due to varying sequence lengths. Layer norm stabilizes the hidden states for each sample independently. The second major component is the feed-forward network. If attention is the social layer, this is the thinking layer. It processes the context gathered by attention. Notice the expansion factor, forward_expansion. We typically expand the embedding dimension by 4x, e.g., 512 to 2048, and then project it back down. This is similar to how a human brain might expand a thought into many details to understand it, then summarize it back. We use a simple linear ReLU stack. Now, the forward pass. This defines the data flow. We accept value, key, query, and a mask. In a standard encoder, these 3 vectors come from the same source X. This is self-attention. We pass them into the attention layer. The result, attention_out, is a reweighted representation of our input. This next line is critical, attention_out plus query. This is the residual connection. It allows gradients to flow directly through the network during backpropagation, creating a gradient superhighway. Without this, deep networks like GPT-4 would suffer from vanishing gradients and fail to learn. We then apply layer norm after the addition. Finally, we pass the context-aware tensor into the feed-forward network. This projects the data into a high-dimensional space, applies nonlinearity, and projects it back. We then apply one final residual connection, forward_out plus x, and normalize. This output tensor has the exact same shape as the input, sequence length, batch size, embedding size. Let's verify our implementation with a sanity check. We create a dummy tensor x with shape 10, 2, 5, 12. That represents a batch of 2 sentences, each 10 words long, with each word represented by a 512-dimensional vector. We initialize our transformer block and pass x as the query, key, and value. When we run this, the output shape perfectly matches the input independent of the internal complexity. We have the chassis, but we cheated on the engine. We used nn.multihead attention, letting PyTorch handle the complex math. In day 3, we delete that line. We will manually code qk-t and softmax scaling from scratch. The code for today involves the entire production-ready block and is in the description. Follow and subscribe to become a 3 Sigma AI engineer. See you in day 3.